Okay. Today our guest speaker is Dr. Karin Pacheco, and she works for National Jewish Health in Denver, Colorado. She's done an excellent study with analysis or diagnosis of metal implant failures. And so I'm going to let you go ahead and give you the floor. Thank you.
All right. So good morning, everybody. I'm Karin Pacheco. My training actually in our division is, so I did internal medicine and allergy immunology, and then went back and did occupational environmental medicine. So we are particularly interested in, if you like, the determinants of metal sensitization and really best ways to measure it. So I'm going to talk today, we've developed, I think, a nickel and a cobalt LPT that are robust. The chromium is problematic, and so if anyone has ideas about this, that would also be helpful. So next slide, please. So this in general is an overview of what we go through in order to develop an LPT. And as I said, we have a nickel, a cobalt, and a chromium, in part because those are probably the most important metals in implant sensitization. So the process in part involves a literature review to get an idea of both the dose range and which metal salt is the most relevant. We look at controls who are unexposed, no history of metal reactivity, no metal implants as a source of metal exposure, and compare it to cases, which in this case we've defined as people who are patch test positive. Part of the problem, I think, in developing some of these tests is what is your gold standard? For the LPT, what is your gold standard? And by the same token, for patch testing, how do you know that what you are looking at is specific to that particular metal? So in general, with nickel, we started out in micrograms per ml. It's nickel sulfate hexahydrate. It's the most common. For cobalt and chromium, we worked with molar concentrations. In general, the way we set up the assays that they're quadruplicates per time and metal concentration. We have 12 unstimulated wells per subject to get a sense for what the background is. We generally look at days 4, 5, and 6 for incubation, although we have looked at 6, 7, and 8 as well, although it looks like 4 and 6 are probably the most representative. We measure incorporation of tritiated thymidine as a measure of T-cell proliferation, and that can be incubated for anywhere between 6 to 18 hours. And then we compare the incorporation of counts between conditions. And I'm sure all of you know this, so I apologize if I'm talking to you about matters that you already have a pretty good knowledge of. The peak stimulation index is the peak count with the metal divided by the peak count of the media only, and then we also compare the range of peak stimulation indices between the cases and the controls in order to set a positive threshold. Next slide, please. You all know the pathogenesis of type 4 hypersensitivity, but the point that I want to make here is that it is the Th1 cell, and in most cases it is a Th1 cell, that we're interested in identifying. We're interested in identifying that T cell that's specifically sensitized to the metal in question. And what is the best way to capture this T cell? Obviously, the two main ways are both by patch testing or by the LPT, and you hope that you're capturing the same cell, that you're measuring the same immune phenomenon when you do so. So next slide, please. So the assay principle for our LPTs are the same as the beryllium, really. You isolate PBMCs, you culture them with nickel or whatever metal, you've established the optimal range, you add a radio label, and the extent of proliferation is considered to be proportional to the radioactivity incorporated, and that's reported as a stimulation index. Next slide. Thank you. So these are just some examples of the patch test positive patients that in this case we're using as a positive control. The point I want to make here is that obviously patch testing is subjective. In order to reduce some of the subjectivity, I use several concentrations of the metal. So in this case, nickel sulfate 2.5 and 5%, or potassium dichromate 0.25 and 0.5%. And in the case of cobalt, there are two salts that are available for patch testing. So we use both the cobalt sulfate and the cobalt chloride because these often serve as an internal control so that what you're looking at you think is truly a positive. Next slide. So the first assay that we developed was nickel. This was the first thing that we published. So this is just some from the initial paper, which really had less than 100 patients. But the patients and the controls, the patients were defined as a positive patch test. The controls had no exposure and were patch test negative. We then went on, the next graph really looks at the concentrations that we looked at between 0.1 and 100 micrograms per ml. The purple squares are the controls. The dark squares are the patients, because the other thing is that you need to look at that concentration where the majority of people will respond, aiming to find a differentiation between the two based on the counts incorporated. Next slide. So this is from actually the optimization paper for the assay that we produced, demonstrating that in point of fact, this is valid and reproducible. So we had anywhere between sort of 40 and 70 samples, and these are all controls, people unexposed to nickel without an implant. And then we looked at what the mean was for each condition, that is to say, this case we decided on days 4 and 6, although we did look at an array. I didn't include all those data. And what is the mean incorporation with the different concentrations? And so then what's the standard deviation? And we used the same conditions as for the beryllium LPT, which is really the mean plus 3 standard deviations, which is why we set the positive threshold at 5.7. Next slide, please. Right. The threshold is really pretty high, and it's higher than, so the major other group that does these assays has set their threshold at 2. We think that threshold's too low because nickel is actually somewhat immunostimulatory. It's probably in part why it's such a prevalent allergen. And then we initially looked at the sensitivity and specificity of the LPT versus the patch test. Again, finding a sensitivity of 68%, much better specificity of 98%. But that's pretty reasonable when you're comparing two measures of sensitization in that way. Next slide, please. So what we did a few years later was to go back and look at, so we then had accumulated data on about 1,000 patients. And so we turned it around and looked at how well the LPT discriminated between what would be considered patch test positive and negative. And this again is another way of looking at the sensitivity and the specificity. And we found that indeed, people who are patch test negative had a mean PSI of 4. People who were patch test positive had a mean PSI of 23. So again, it makes us feel that the assay that we've developed was adequate to discriminate between another measure of sensitization. Next slide, please. The other thing that we looked at was just looking at the distribution of PSIs by the interpretation. Again, were they significantly discriminatory? And in this case, we looked at those people considered abnormal, which would be 2 counts above the threshold of 5.7. Those that would be considered borderline, which similar to the BELPT is 1 condition greater than the threshold but not 2, and then the normals. So what's interesting to me here is that the borderlines have a mean PSI of 11. So what that says in a way is that it really is a mixed population. I think it would be nice to say, oh, all the borderlines really are just normals. They had an aberrant reaction. I don't think that's the case. I think that the borderlines truly involve people who are true positives and also people who are probably false positives in that setting and probably normal. So often what we do when we get a borderline, especially in the context of the clinical history, would be to repeat the assay to see what we get. More often than not, we get normals, but we do get a number who are either borderline again or are now abnormal. So it's still a condition that I think is not well defined clinically. Next slide there. So this is just to let you know what we did for the Cobalt LPT was to go back and look at the literature for other assays that had been prepared, looking at what was their cell concentration, right? What was the volume in which they performed the assay? Did they have positive and negative controls? What salt did they use? What concentrations did they look at? How did they incubate it? Are there conditions that are similar enough that we could then use it to develop our own assay? And the next slide is just a continuation of some of the other papers that we looked at in terms of developing such an assay. Next slide, please. So this again is really taken from the initially setting up the assay in terms of what conditions we looked at. So we looked at a dose range of between millimolar to nanomolar. We looked at a time course because it would be possible that the reaction to cobalt per se might be different. We looked at controls, non-exposed, no symptoms, and positive controls, patch test positive. We looked at whether or not cobalt chloride or cobalt sulfate was a better salt. And then we looked at the various conditions. And so the next 3 slides I just want to show looked at some of the conditions that we evaluated. So next slide, please. Again, this is cobalt chloride versus cobalt sulfate using 2 controls that were patch test positive. Unfortunately, it illustrates the difficulty of setting up the assay because we had patient 1 really responded well under all conditions and really with almost all salts. Patient 2 did not. So patient 2 here responded to the cobalt chloride. You can see the little orange diamonds looking at the PSI, but did not respond to the cobalt sulfate on day 5. The next slide is day 6. And again, you can see that patient 1 in the purple responded well to both conditions, and patient 2 looked no different than the controls. The next slide, on day 7, you can see that patients 1 and 2 responded to the cobalt chloride and to the cobalt sulfate after 7 days of incubation. And so this is basically the reiterative process that we went through to try and develop the cobalt assay in a way that would produce a valid result. Next slide, please. This is just an aggregate of the data looking at, if you like, the PSI of the cases, comparing the PSI of the controls, using 3 different doses and 3 different time periods. And and I don't have the N here. I don't recall exactly how many that represented. The pattern that you see actually, I think is kind of interesting in that over time, the controls really didn't respond to the cobalt, and their PSI dropped over time. The cases, on the other hand, in 2 out of 3 of the concentrations, the PSI went up, and it went up over time. Again, an indirect measure, the pattern being an indirect measure of the stimulatory capacity of the metal salt. So I think the next slide is our, so this is the same set of graphs similar to what I showed you for the nickel. Again, looking at the dose range on days 4 and day 6. We decided to go with day 4 and day 6 because it pretty much matched what we did with the nickel and also matched what we did with the cobalt, meaning we could use the same setup for the 3 different metals. Again, showing you what the mean was, what 3 times the standard deviation was, and then being able to set a threshold. So we used 10 to the minus 5, 10 to the minus 6, 10 to the minus 7 concentrations. And you can see here that we again set the threshold at a mean plus 3 standard deviations. Again, it's not quite as clean as the nickel because we clearly do have some people that respond above that threshold, but not many. Next slide, please. I think. Yeah, so I went back and did the same analysis as I did with the nickel. So considering patch test positive cases, patch test negative controls, did the PSI for these 2 conditions adequately discriminate between the 2 conditions? And I think this really shows that, in fact, it did. So the mean, but again, the mean for the cases was not very high. The mean was 2, or on day 6, 3. The controls, though, had a PSI about 1, which is what you would hope for if the cells were truly not responding to the cobalt. The next slide talks about chromium, and we have had problems with this. We used the same approach, right? So PBMCs separated by phycohypake, resuspended in complete medium, plated. We used chromium sulfate in this case to quadruplicate wells at, again, a similar dose range. You want the dose high enough to stimulate, but not so high as to be toxic. And again, not so low as to be so low that no cell, even the sensitized cell, is not going to respond. Same controls of PHA in Canada, incubated for 4 to 6 days, pulsed for 6 hours, and then looked at the cell proliferation. Next slide, please. So again, this is the same kind of plot for chromium, but you can see, especially on day 6, that the results are kind of messy. There's a much higher range. We, again, settled on concentrations of 10 to the minus 4, 5, and 6, plus 3 standard deviations gives us a threshold of 1.9. But in this case, such a threshold did not discriminate very well between the cases and the controls. And I think that's obvious in the next slide, which, so we looked at an initial cohort and a validation cohort. We compared their demographics, which were very similar. The initial cohort, so we had those who were truly non-reactive, those reactive, and those borderline. And then we went back and looked at the PSIs of people who were chromium patch test positive and negative. So if we just look at the LPTs, it does look as though the assay can really discriminate between groups of patients. But if you looked at the chromium patch test as the gold standard, it didn't really. So people with a negative and positive patch test didn't really have very different PSIs, and in fact their PSIs were the same in the validation cohort. So next slide, I think, demonstrates this better. Looking at, and again, I don't have the end here, but looking at the PSIs of the controls and the positive patients, you can see that many of the patients reacted in the same ballpark as those of the controls. So this really was not a very sensitive LPT, was fairly specific, but not an assay that we feel very comfortable putting out there yet, because I think we'll miss a fair number of true positives. So next slide. So these are our conclusions. Developing the nickel LPT was relatively easy. I'm actually glad we started with that. It really does discriminate well between the positive and the negative controls using the patch test positive cases. Again, because the threshold is higher than these other metals, it's possible that we may miss some true positives, but they seem to match fairly well with the patch test positive patients. I will say, though, that we still find people who are clearly positive by the LPT and who are negative based on the patch, and vice versa, where we have some clearly positive patch tests and the LPT really is not positive and does not discriminate. I think part of it relates to, these are two different measures. It's possible that in whatever blood sample we got, we didn't capture enough of specific T cells to be seen in a positive assay, and or we have skin that's been tanned or is just not really reactive, and so we miss the patch, but we get it on the LPT. The cobalt, because cobalt is really less common an allergen, we are seeing the data that have been previously published that about 30% of people who are nickel positive are also positive to cobalt. But again, the prevalence of sensitization to cobalt is just a lot lower than the nickel. And as I said, the chromium is problematic. The negative controls cluster fairly well, but if you set the threshold based on the negative controls, you don't really discriminate a lot of positive patients. Now, it's possible that in this setting, the chromium sulfate that we're using is the wrong salt. We get much better patch test responses to the potassium dichromate, and that's the patch test reactions that I showed you towards the beginning of this talk. But we can't, it's too toxic to use. So we're considering whether or not we can try using sodium dichromate, which doesn't have the same toxicity profile. And maybe if this would be a better approach to get a more discriminatory LPT. So the last slide just sort of acknowledges that many people who worked with this, Vijay and Knight really developed most of the assays. Obviously, Lisa has been enormously supportive in developing these metal LPTs. Lisa Barker, of course, is critical. Sam Erb and Gina Mondella have been our research coordinators, and Claire Koshot is the new sort of head of this metal LPT process. And again, Trish Merkel and Molly Wolf, we've also worked with pretty closely to develop these LPTs. So that's it. That's it for the talk. So I'd be happy to answer any questions.
Okay, thank you, Dr. Pacheco. I think I'm going to stop the share and open this up for questions. We have a lot of people who are muted. So if you want to talk, you'll need to check that. So is there questions for Dr. Pacheco?
I have a question.
Okay.
Karin. Thank you, Karin, for your marvelous work. I know how much work there is behind the results.
Yeah.
It's how much that is a laborious test. The beryllium, we make the same process with beryllium, but with the Melissa, we took the assay ready to go. The work that you show us here was done by Vera Stehal, that she implemented the test, and she performed all the studies that you have shown here for all the methods. And so we took the assay ready to go, and we rely on the hard work that Vera performed to put this assay in use for laboratory use. Regarding the chromium, Vera was using the chromium chloride. I don't know if you try this. That's the chromium that we are working with.
So what chromium salt did she use?
Chloride. Chromium.
Really, chromium chloride. Okay.
I don't know if you have tested this.
No.
It's working. It's working and working very good. So perhaps you can test this.
Yes.
Regarding the cobalt, we are using the cobalt chloride again. Nickel again, nickel chloride. We don't test any other salts.
So you use chloride salt for all three?
Yes, and that's what Vera, I say again, we rely on Vera experience, and we took the Melissa test ready to go.
So I have a question about the Melissa. What exactly does it measure? What is measured?
It's measuring exactly what is measuring the BLPT.
So it's measuring
the proliferation of the CD of the T cells, CD4. What we are dealing with the type 4 hypersensitivity.
So it's measuring counts? It's measuring CPM?
Counts, yes. We're using the tritium. It counts, CPM, exactly as you did, or how we did for the beryllium. We are using the same tritium for beryllium and for Melissa. We are incubated only 4 days. Again, I have no comparison. The beryllium we are doing 4 and 6 days. Yes, because it's what I took from National Jewish, the method from National Jewish. But again, we are not incubated more than 4 days. We are looking for those metals that cause sarcoidosis, especially. From all the metals that you showed, the cobalt induced granulomatous disease. We are looking for zirconium, titanium, all those metals that in patients with BLPT negative and still they have a granulomatous disease. So we are not looking so much on nickel and chromium.
I see.
Because I don't know, perhaps I missed this. What is the diagnosis of your patients? The patients that were tested, were all of them with implants?
Most of them, actually, they had both implants or were tested preoperatively because they had a history of metal reactivity. And that's why they were referred.
I understand. So they have no lung disease?
No.
I understand.
So the exposure is different?
Yes, we are testing a different cluster of patients. I understand now. Okay, we are testing patients with the lung disease, And because we are the only center in Israel performing MELISA, so and we have referral also of dental implants, orthopedic implants, but that is the minority. So I really understand how much work is behind this presentation, and it's very nice work. Did you publish the Cobalt and the Chromium?
No, we need to do that, and probably looking at the chromium chloride is that may help us, I think.
Yes, perhaps, because you know, in the MELISA test we have a value that is toxic. So when the chromium, when the metals kill the cells,
right?
And we don't have with the chromium chloride this effect. Perhaps you can. Yes, I cannot say we have a stock solution and a working solution, but again, that is ready to go. The work was done by Vera, and we took this already like this, so we didn't change the MELISA test anymore.
So I don't know that much about the MELISA. What did they use for a positive control?
PHA and pop with mitogen.
But in order to decide if somebody's positive or negative, how did they set the threshold?
We have 3 concentration for, PHA we didn't use. That is for beryllium. The threshold is for all the metals, and also for the threshold is 2.5, and positive for pop with mitogen is above 5, the stimulation index.
What is 5? I'm sorry, I didn't.
The stimulation index
is 5 for what?
Yeah, for proliferation. So without pop with mitogen and with pop with the SI is exactly as for the metals.
So the threshold is 5.
But in general, when is above, is near 5, we repeat the test, because we have a lot of patients that are steroid dependent. So also when they stop the steroid for a while, still there is an effect. So the washout of the steroid is very, very important. And we want a much better positive control than 5. So that is very borderline, and we try to wash out the steroids of the patients.
So if the PSI is below 5,
we repeat it. There are immunosuppressed. We don't like this. Okay. So we want a pop with mitogen about 100, and we have this 100, 200. So that is a very nice positive control. When I went to Geneva to see how the tests worked, and Vera came to Tel Aviv also, and that are the positive controls that Vera likes, above 200.
A PSI above 200?
Yes.
Wow, that's impressive.
So that is. We have a lot of problems with the pop with mitogen. The stock lost the activity very, very fast. We have a lot, and there are lots that they are not working.
For beryllium, so you're saying?
For beryllium, we have PHA and pop with mitogen. With the positive controls, we have a lot of problems. Really? Try to keep on the same lot, and sometimes the lot doesn't work. So we repeat this with other lots. We have problems with the positive controls in chronic, in the LP also.
Yeah. So what's interesting is that we had when we first started out with nickel, it was working great, and then all of a sudden, it wasn't.
Yes.
And we found actually that the stock solution had gotten diluted.
Yes.
And so periodically we have to go back in and verify the concentration, etc.
Exactly the same. that is something magic from the science. We cannot understand why it doesn't work.
Right.
When it works, it works. But when it doesn't work, it's very difficult to find the reason.
Yeah.
Because we have to go to different lots of positive controls, and as you told, to go back to the lot to the stock and to
Right.
that is a very, very problematic test. Also, the Melissa, we are working a lot. Sometimes we repeat the test for the patient without any, the HMO in Israel are covering the test, but the second test is not covered.
Oh, I see.
But we repeat this because we are dealing with poor people, that want compensation. So it's not trying to make money from this.
No. I understand that. And yeah, we have to do that too sometimes. To repeat if it's uninterpretable, we just repeat it and don't charge for it because it's some sort of lab error, although we don't always know why.
Just concerning the positive controls, we also use in our BLPT 2 different controls. And it seems to me that the reactivity to the positive controls is also patient dependent. Sometimes we have patients reacting to PHA, but not to CON-A.
Yes.
And sometimes it's vice versa. And I understand why.
Right.
I do not understand why.
No, I sometimes I think it may be the stock solutions that may be.
Yeah, but in other patients it works. That's the point.
Right. I know. And there are some people who respond to we use PHA in Canada, and some people don't respond to the PHA, but they have a huge response to the Canada. So yeah, I mean, yeah.
That is
patient.
Okay. Yeah. But depend on the immunocompetent if they have under steroids or other no.
You don't do it under steroids.
Okay.
I do. Okay, if it is not possible to get the patient clean of steroids, we do it below 10, which is a certain dose with some patients or some sarcoidosis patients have to live with. But normally I require them, please cut off steroids for at least 4 weeks. Yeah. Otherwise, the point is you may have positive results and everything is clear, but if you have a negative result, what are doing then?
Exactly. Yeah.
But I do have another question concerning your methods. You also try to set up cobalt and nickel LPTs and different. So you may use chloride or sulfate or whatever, but if you put it in your cell culture media, you have phosphate in, and very often you have metals forming non-soluble, soluble phosphates, which are not digested by the cells. So is this a problem? I ignore that in case of beryllium because it's also the case with beryllium. But it seems that it works. But how is it with nickel or chromium or whatever?
It's something that we've sort of thought about, because theoretically any salt should dissociate in solution, and so it shouldn't matter if it's sulfate or chloride. But I think it probably does matter. The nickel, we use nickel sulfate hexahydrate, so that's easy. Because that will dissolve really pretty well, and so maybe that would be an easier salt to work with. The cobalt, there didn't seem to be much difference between, we did cobalt sulfate and cobalt chloride, and that they also seem to dissociate. The chromium may be a problem because of the salt that Lizzie really mentioned, that maybe we should be using either chromium chloride or, again, sodium dichromate. That's another question that we sort of have related to the salt. Does it matter if it's the cation or the anion? And I don't have a good explanation. I don't know. But again, sometimes if your assay is not working well, trying a different salt may help. Again, we've had really good luck with the nickel sulfate hexahydrate because it's already sort of hydrated. So it dissolves really quite well.
So I just have one comment about the ionic state of the element in question, and there are these pictographs or where they have the proteins and the negativity or positivity, and those associated like with Blue 69 or not.
Crystallography structure.
And yeah, thank you so much. Yeah, the structure, and so they think it's a pocket of electronegativity. Lisa, can you correct me? And that really,
Yeah, -9, right?
Mhm.
So they think that particular groove for beryllium, but we don't. We know some of that about nickel, and Karin can share with you some of the research we're doing on the more basic science. With CU, we have a colleague at the School of Pharmacy that we've been working with on some of the major histocompatibility complexes that might be associated in nickel. And I don't know if Kathy, did you have more to add? Because I think Karin can say a little bit about that.
well, the only thing that I was concerned about is if you're using, salts that might have different ions.
The
positive charges
of
of
the
it.
metal from the salt may affect its ability to be taken up and
Right,
presented.
right.
Yeah, nickel's hard because it's, as they say, is promiscuous. Which may be why it is such a prevalent allergen, right? What we have found, which again we're sort of verifying in a bigger cohort, is that HLA-DR53 presents nickel really well. And it seems to associate with nickel sensitization in people who have an implant. It doesn't discriminate sort of beforehand, pre-op patients. There's really not a difference in the distribution. But the post-op patients who have a nickel implant and they're reacting to it are much more likely to have DR53. And so in that sense, we interpret that to say maybe it's much more efficient at presenting nickel in a setting where you already have a source of nickel, and you're reacting to it in the context of the joint and the bone marrow, right? Which is, again, this is sort of an offshoot of that. Implants are interesting because they're implanted into bone marrow, and so they're implanted into an immunologic agent right there, and able to respond to it, which that makes it somewhat different than, say, the lung, right? In terms of the way it's absorbed, the way it's presented, and the nature of the response.
So I have one more unsophisticated question, I have to say, because, you see the difference in the nickel patch test versus your test, and they don't always coincide. Is there maybe two different mechanisms?
Yeah.
Okay, and so that, if people are sensitized through skin, maybe they're not so able to be shown to be LPT positive, just because there's two different mechanisms that are going on in the body.
Possibly, although, and that's the argument that orthopedists made. Well, the joint is so different, you can't measure it, on the skin. You have to assume that the immune system is system-wide, right? Otherwise, it doesn't work. And the example that I always bring up is that if you think somebody has TB, what do? You do a PPD on the skin because the immune system is system-wide, right? And so it's not entirely clear to me that the patch test measures something that much different than the blood. And both have their own variables.
But one additional question, it may be that the patch test doesn't measure something different, but the way how, for example, nickel allergy evolves is something different from that. of the hypersensitivity evolving from an implant, isn't it? You have as I'm not familiar with nickel allergy, but if you have discussions with the dermatologist, they presume that you have a protein binding nickel and acting as an haptene or allergen. So it's not nickel alone, but you have a protein nickel complex, which is immunostimulating. Is it the same in an implant?
I don't think we know, to be honest. I also think that it's not any one particular peptide either. So I think that there are many different ones for nickel for whatever reason.
Yeah.
But I don't think it makes sense a priori to say the patch test is unable to measure the process in the joint.
Okay.
But there's slight variability, and that sort of speaks to that first slide I stuck in there, which is to say, what you're really interested in is finding that T cell, and what's the best method for finding that T cell.
Another question, perhaps you mentioned this. Did you perform the blood test first and the patch test second? Because by stimulating the skin can be also a stimulation in the blood, so a false positive.
No, we actually do the blood test first, mostly because it takes a couple weeks to get back the result. So we try and get people to do the blood test first and then the patch test. We've also looked to see, do people with implants, are they more likely to have a positive blood test because they have a source of nickel? And that's not the case. You know, it would be nice if it were, because it would make more sense. But it's not always the case. I just saw someone yesterday who literally had negative patch tests, and her PSI for nickel, remember the threshold is 5.7, was like 100.
Mm-hmm. Well,
You know, and I do not have a good explanation for why that happened.
So Lizzie, one of the things that we've done is, as Karin said, we always try to get someone's LPT done prior to their clinic visit for patch testing. But if we can't, we draw the blood the first day before the patches are placed. That's just one of the clinical research protocols that we follow to try and ensure that we're not doing what you're concerned about.
Right.
Well, that was a very great discussion. I had maybe saw a few light bulbs go off here, so I'm very pleased that your presentation, Dr. Pacheco, opened up a lot of questions and people having some answers, and then
I got some really useful information, so I really appreciate that.
That's the reason this group has been started, is because we really need to share with each other so that we can progress quicker than we have in the past. Although the work has been really done, done well. A lot of work has been done. So I have just two things I'd like to mention to this group. I'd like to do a little bit of cross collaboration between the two groups that I have. I have a working group on real-time detection methods, and that group has a great deal of experience of going into the field and finding beryllium exposure risks in a large, different, broad range of industries. And so I would like to have a couple of the speakers who have done a lot of field studies, for instance, Mike McCulley, possibly David Brissett with INRS in France, give the next talk for this group. And I'm going to say I'd like to take a little 2 months off, and let's start it in January, if that's okay, just because there's so many holidays, time off during these next 2 months. And so I'll send out the announcement for the two groups to join in at our next meeting. Then the other thing, I had a request from this group, or maybe just to stimulate some ideas and thoughts, is that I've been looking for a laboratory that conduct confidential genetic testing for new hire workers, and I'm having a hard time finding this. And I thought, so I'm a participant in 23andMe, and they have this great program where you take a survey and they ask you if you have these diseases or these characteristics. And then it's really very powerful because they can find, markers for diabetes or eye neurological eye problems, things like this. And so I'm wondering if we can't get some power in genetic testing and the confidential surveys that the employees could participate in to see if we can figure out what's causing sarcoid, sarcoidosis, and then also beryllium disease, they showed what kind of symptoms they have. So it's, I don't know. If you guys have any ideas or laboratories that you would know of, that especially in Europe, that I could point these clients to, I would really appreciate it.
May I add directly? So we did some genetic tests on sarcoidosis together with colleagues from Kiel, northern Germany. So we collected a lot of sarcoidosis patients and did the so-called GWAS, genome, what's the name?
Wild association test.
Thank you. And and some of the risk genes popped up which are associated with sarcoidosis. And currently we're working to elucidate what is maybe the role of these genes in sarcoidosis.
Okay.
That is interesting work. Yeah.
Dr. Zissel, your lab could do Glue69. Your lab could probably do that.
No, we do not do any genetics.
Okay.
This has been done in Kiel.
Okay.
I can give you, if you're interested, can give you contacts.
Please do. I really, really appreciate it.
Yeah, I do.